So, recall the Taylor series is a polynomial expansion of a function f of x around a value, and it can be given in this form. A Maclaurin series is simply a Taylor series where a is 0. So it's just a Taylor series where you're expanding around 0. To expand around 0 because that's a place that a lot of people often have a lot of interest in, and it gives a standardization for expanding a function. So if you type in Maclaurin series of functions, you can find the Maclaurin series for a lot of functions. This is on Math World. You can find the Maclaurin series a whole bunch of different functions. So in this video, I'm going to go over some examples, finding the Maclaurin series for functions, and just look at the graphs of them, just so you can get a feel for what's happening. So let's work on some examples finding the Maclaurin series for a function. So here we have f of x is equal to 1 over 1 minus x, which is equal to 1 minus x to the negative 1. So that makes f prime of x equal to negative 2, negative 1, 1 minus x to the negative 2 times negative 1, right? So it's the outside, and the inside is negative x, negative 1. So this gives us 1 minus x to the negative 2. Then our second one, we have f double prime. That's going to be negative 2, 1 minus x to the negative 3 times negative 1. And that's going to be 2, 1 minus x to the negative 3, f triple prime. So it's important when working on these, one thing that is helpful is to notice a pattern. So here we're going to take the derivative of this, which is going to be 2 times negative 3, 1 minus x to the negative 4 is equal to, the derivative of the inside, 1 minus x, is negative 1. So that's going to be 2 times 3, 1 minus x to the negative 4. And let's do one more just to make sure that we can see a pattern. The derivative of this, I'm going to pull out 2 times 3 times 4, 1 minus x to the negative 5 times negative 1. That's going to be 2 times 3 times 4, 1 minus x to the negative 5. And so at this point, it might you might see the pattern as being the ith derivative of x, of f of x. So the ith derivative of x is going to be, so this is the third derivative, this is 4 factorial. Sorry, this should be the fourth derivative. This is the third derivative, 3 factorial. Second derivative, 2 factorial. First derivative, 1 factorial. Fourth derivative, 4 factorial. So this would be I factorial. And then here we always have a 1 minus x. Fourth derivative, fifth to the negative fifth. Third derivative to the negative fourth. Second derivative to the negative third. So this is always going to be negative I plus 1. So if we were to write out the Maclaurin series, right? So we have f of x is going to be I is equal to 0 to infinity of f of I to the x, not to the x, f of I of x, I factorial times x to the ith power. We know what the, sorry, this isn't to the x, this is 0, right? So we know what f to the ith derivative is. That is going to be that's going to be I factorial 1 minus x. Sorry, right? So this is the ith derivative of 0. So x is 0, and that is all to the negative I plus 1, x to the ith, all over I factorial. And if you notice, we have an I factorial down here and an I factorial up here. So those are going to cancel out. You're going to have an I equals 0 to the from 0 to infinity. 1 minus 0 is 1. So we have 1 to the negative I plus 1, x to the ith. 1 to the anything is going to be 1. So we end up with this function. So we have 1 over 1 minus x is the same thing as just adding up all the powers of x. And so I'm going to put this in a graph just so we can see that this is Algebra, which is a free graphing software. You can download it if you want. So I'm just going to put in the function we just did, which is 1 over 1 minus x. And you can see that show up there. The point we are expanding around is at 0. So I'm going to put a point there. The first expansion, so f of x, sorry, let's say f0 of x is going to be, so the first value is going to be x to the 0, which is just going to be 1. And then our next value is going to be x, is just going to be x. Our next one is going to be x squared. Then, whoops, x to the third. Whoa, that's not right. Plus x to the third. And you can see every time I add a power of x, it does seem to be getting closer and closer. So I'm just going to keep going. 5th, 6th, 7th. And you can see that it keeps getting closer and closer. 8, 9, 10, 11. Whoops. X to the 11th. Yeah, you can see it goes all the way from here, and it looks pretty close for after it. If you do all the way up to x to the 50th power, you can see that it is spot on all the way almost to -1. So, yeah. Now I'm going to go through the Maclaurin series of sine of x. So, f prime of x is going to be cosine of x. This one you might be able to do in your head. So you're going to have negative sine of x. F triple prime is going to be negative cosine of x. F fourth prime is going to be sine of x again. And then f to the 5th prime of x is going to be cosine of x. And so if you notice, we ended up with the same thing we started with, so it's just going to do this pattern forever. So we're expanding around a equals 0. So f prime of x at, so cosine of 0 is going to be 1. Sine of 0 is going to be 0. Negative cosine of 0 is going to be -1. Sine of 0 is going to be 0. And then we go back to 1. So the series for this is going to be the sine of x is going to be, so our first term is going to be f of 0, so sine of 0 is going to be 0. So we're going to have 0 for our first term, 1 over 1 factorial x plus 0 over 2 factorial x squared plus negative 1 over 3 factorial x to the third plus 0 over 4 factorial x to the fourth plus 1 over 5 factorial x to the fifth. And if you notice, every other term is going to be canceled out because it's going to have a 0. And out of the terms that are left, every other term is going to be negative and positive switching. So we can say the sine of x, just to simplify things, is going to be 1 over 1 factorial x minus 1 over 3 factorial x to the third plus 1 over 5 factorial x to the fifth minus 1 over 7 factorial x to the 7. So we're only doing the odd numbers, and we are switching the sign each time. So 9 x to the 9 dot dot dot. And you could write that as sine of x is equal to I equals 0 to infinity. So we're going to want, at 0, we want this to be positive, so we're going to say negative 1 to the i-th power times, just so we have that alternating sign, 1 over, and since we want all the odd numbers, we can say 2i plus 1, and that would give us all the odd numbers, right? Because if you put in 0, you get 1. If you put in 1, you get 3. And then times x to the 2i plus 1, right? So this gives you all the values. This also gives you all the values. And if you look up on Math World or wherever you want to look up online, you can see that this is in fact the formula for the sine of x. So this is the last example I'm going to go through. F of x is equal to sine of x, cosine of x. So let's just find the derivatives of these first. So I'm going to say f prime of x. We're going to get the derivative of this. Let's go with the derivative of this, which is going to be cosine times that. So we're going to get cosine squared of x plus the derivative of this, which is going to be negative sine. So we're going to get negative sine squared of x. So if we find the second derivative, we are going to end up with the derivative of cosine squared. We're going to have 2 times cosine of x times negative sine of x plus, minus, because of the minus, 2 sine of x times cosine of x. So just to rewrite this, that is negative 2 cosine x sine of x minus 2 cosine of x sine of x. So this is equal to negative 2. Sorry, these are the same, right? So we can say negative 4, actually, cosine of x sine of x. So with these problems, it is usually easy. It's really nice if you can find some sort of pattern. So I can see if I take the derivative of this, I'm just going to end up with this. Then I take the derivative of that, I'm just going to go back over to here. So I can say f to the triple prime of x, that's just going to be negative 4 times, and then I already did the derivative of this up here, cosine squared of x minus sine squared of x. And then I already did the derivative of this right here. So I know f to the fourth of x is going to be negative 4 times negative 4 times cosine x sine x. So we can see that it's just going to be repeating back and forth. So if we put in a 0 for these x's, right, because we're expanding around a equals 0, this term is going to go away because of the sine of x equals 0. This term is going to go away because of the sine of x equals 0. This term is going to go away as well. So you can see we are going to just keep alternating between positive cosine squared of x minus sine squared of x, and then for sine squared of x minus 4 cosine squared of x, and it's just going to keep going up by multiples of 4. So we can say that sine of x, cosine of x, so the first term is going to be 0. The second term is going to be, so let's just do this now. If we put in a 0 for this, we're going to get, this is going to be 0, and we're going to get a positive 1, right? If we put in a 0 for this is going to be 0, and we're going to get a negative 4. So we can start to see a pattern here, and we can say the second term is going to be 1 over 1 factorial x, and then we skip the x to the second term, we go x to the third, and so this is going to be minus 4 over 3 factorial x to the third. Then we're just going to go back to plus, we're going to multiply this by a multiple of 4, so 16 over x to the, 16 over 5 factorial x to the fifth plus, 4 to the third over 7 factorial x to the seventh, plus minus plus minus, dot, dot, dot. And we can look at this in a graph and see if that is in fact true. Sine of x in orange. So if I test the function that we came up with, I'll just say this is f of 0 of x. And then our first term was 1 over 1 factorial of x, then minus 4 over 3 factorial of x to the third plus 16 over 5 factorial x to the fifth, minus 4 to the third over 7 factorial x to the seventh. So those are just the terms that we came up with, and you can see that it does look like it is approximating this function the farther we go.